This is the draft of a conversation about power in AC steady state. Consider this situation. We have a source that is feeding a load. The load could be as simple as a resistor or as complicated as a whole town. The important thing is that the voltage in that load is a sinusoidal function of time with a peak value √2 V. What does it make V? V would be the RMS value of the voltage, right? Would be the reading of an AC voltmeter set across the load. V is the RMS volt. And that voltage will establish a current in the load that is also sinusoidal with the same frequency and with a peak value √2 times I. I who? I the RMS amps of the current flowing into the load. Please observe that the phase of the voltage identified with the lowercase Greek letter alpha and will always be alpha in these videos. And the phase of the current is veta. Will always be veta. Let's visualize alpha and veta because they are very important. Allow me to represent the voltage, the function of time V of t, and the current with phasors. There you go. V alpha and I veta. You say, hey, wait a second. You are using the RMS value of the volt? That's right. I'm representing the voltage and the current functions of times with RMS phasors for reasons that will become evident pretty soon. Graphically, those two phasors look like this, the voltage phasor and the current phasor. If this is a real axis, we can see clearly what is the phase of the voltage alpha and what is the phase of the current veta. There is another angle that will become very important to us in the near future, alpha minus beta, theta, the angle between the voltage phasor and the current phasor, alpha minus beta. That angle we will call the power factor angle. Let's go back. We want to compute what is the power absorbed by that load. Multiply V times I. V times I, right? Yes, V times I. Obviously a function of time. But we don't see clearly what is happening with that one. Allow me to copy that to the top of the next slide and manipulate that a little bit. We remember from high school that the sine of the sum of two angles can be expanded like so. Let's apply that here and there. And then the instantaneous power formula becomes this one that apparently is more complicated, but we can isolate the effect of time to three places. Here in this sine square, here in this cosine square, and here in this product of sine times cosine. Let's copy that to the top of the next slide. There are other three identities we've learned in high school that let us replace sine square, cosine square, and sine cosine by functions of twice the angle, by functions of 2 omega t. After simplifying the formula a little bit, we get that the power as a function of time in an AC load is the sum of two terms, a constant term, Vi cosine alpha minus beta, and a sinusoid, a function of time. Very often we're interested in industry in what is the average of the power absorbed by a load, by a customer. Why? Because we multiply that average power by the time of service and we get the energy we can bill the customer for. What is the average of that power? Well, the average of that power is the sum of the averages. Would be the average of the first term plus the average of the second term. The average of the second term is 0 because that is a sinusoid. The average of the first term is itself because it's a constant. So the average power is Vi cosine alpha minus beta. Let's put that in words. The average power in an AC load is the product of RMS volts, RMS amps, and a cosine. Cosine of what? Cosine of the angle between the voltage and the current. Look, the average power is the product of RMS volts, RMS amps, and the cosine of the angle between V and I. That angle has a name. That angle is theta, the power factor angle. Let's plot that curve to see if we identify some other phenomena. Curve, I see three curves. The black one. The black one is the voltage. And the blue one? The blue one is the current. The red one is power. The red one is power absorbed by that load. Observe something. Between this point and that point, the absorbed power by the load is positive. And between this point and this point, the power absorbed by the load is negative. What does it mean? It means that between this point and that point, the load is absorbing energy. But between this point and that point, the load is delivering energy to the system, to the generator. How is that? Energy. How can you see energy from this plot? This plot is of power. Let's remember something we have seen before, right? Energy and power. Remember that power is dW dt, but energy is the integral of power with respect to time. Energy is the area under the power curve. Or better, let me plot there the power. In that curve, the first thing I'm going to do is identify when the power is 0 in the element. A, B, and C are the points in time when power is 0 in that load. Between A and B, the load is absorbing energy. What energy? This green energy. And between B and C, the load is delivering that little purple energy. So let's give them names. This is absorbed energy, and this is delivered energy. Where does that energy come from? The truth is that the load between A and B is absorbing a chunk of energy that it has no plan on returning, and also stores away a little bit of energy that it will send it back to the generator. It is as if the load is playing ping pong with that little purple energy. Every cycle, it takes a lot of energy, uses up a lot, and stores away a little bit, what I wrote here as ping pong energy, and then between B and C, it sends back to the generator that little ping pong energy. Energy, that is ping pong. Where does that load keep that ping pong energy? Let's see. The ping pong energy goes to the electric field of capacitors. Remember there is energy there? The energy in the capacitor stored in its field is proportional to the square of the voltage in the capacitor. But this is AC steady state. The voltage in the capacitor is a sinusoid, that white curve. So when the voltage in the capacitor goes from 0 to a peak, the energy inside the capacitor increases because the capacitor is absorbing energy and storing it away. But when the voltage in the capacitor decreases from a peak value to 0, the capacitor has to let go of that energy. The capacitor delivers energy. That's where the ping pong energy goes to the electric fields of capacitors. In a similar way, we can compute also the energy stored in the magnetic field of the inductor. Capacitors and inductors, they store energy that they return later. What this means is that the inductor and the capacitor are ping pong players. And they don't play with the ball, they play with energy. Sometimes they play among themselves, sometimes they play with the generator. So the customer will insist on the company to charge him or her only for the average power because that represents the energy that he actually never returned. But the company will say, no, sir, you may have kept that, but that ping pong energy that keeps traveling back and forth between my generator and your load is using up the windings of my generators, the windings of my transformers, the cables that I connect the generators to the transformer and the transformer to your load. You have to pay for the extra money that I have to invest in my equipment to carry that ping pong energy. Let's have a look at that again. When we have energy that is moving from one place to another, we have power. We divide the energy that's been moved and divide that by the time that it took to move that energy, and we get power. That energy, the ping pong energy, let's give it a more proper name. The energy is stored in inductors and capacitors. Inductors and capacitors as a group are called reactive elements. So instead of ping pong energy, let's call that reactive energy. And the travel speed of that energy between generator and the reactive elements, let's call that reactive power. We divide all the ping pong energy, all the reactive energy by the time C minus A. Let's write it down. The reactive power is the ratio of all the power that travels back and forth as ping pong between the generator and the load in a power cycle divided by the length of the power cycle C minus A. But that ping pong power in reality is twice the purple area. If you do the math and simplify that Q, that reactive power, is VI sine of alpha minus beta, VI sine of theta. That is a computation for reactive power, the power that corresponds to the energy that ping-pongs back and forth between the generator and the inductors and capacitors in our load. We have seen that power is a function of time, and we have defined a few names already. Let's continue. The product of the voltage we read from the voltmeter and the amps we read from the ammeter, that product we will call apparent power. The active power is a fraction of the apparent power, and the reactive power is also a fraction of the apparent power. What fraction of the apparent power is P? The cosine of theta. That's what we call the power factor. The cosine of the angle between the phasor of the voltage and the phasor of the current. Power factor, a number between 0 and 1 that tells us how much of the apparent power will become active power. We could also define a reactive power factor, sine of theta. That angle theta evidently is so important that we better have a closer look at it. That is the voltage phasor, the current phasor, and the real axis. The phase of the voltage, alpha, the phase of the current, beta, and the angle between them, alpha minus beta, theta. That has a name too. That is called the power factor angle. Observe we have defined a few names corresponding to this part of the course. Apparent power, RMS volts multiplied by RMS amps. Active power, reactive power, power factor, and power factor angle. Observe one thing. For an inductive load, the current is lagging behind V. That means that beta is smaller than alpha, and theta is a positive angle. Positive angle, what is the implication of that? The implication is that sine of theta will be positive and Q will be positive. An inductive load absorbs positive Q, positive reactive power. When the load is capacitive, then the opposite happens. In that case, the current is leading. Beta is greater than alpha, and theta turns out to be a negative angle. And the implication, sine of theta. Sine of a negative angle will be negative and Q will be negative. A capacitive load absorbs negative Q. We'll talk more about that. A word about units. Apparent power is represented in volt amperes, VAs, kVAs, MVAs, GVAs. Yes, I know it's volts, temps, amps, should be watts, right? This is a convention. Active power in watts, kilowatts, megawatts, gigawatts. Reactive power in volt ampere, reactives in VARs, kVArs, megavars. The power factor can be written either in per unit, for example, 0.8, or in percent, 80%. But we always have to tell, together with the value of the power factor, if the load is inductive or capacitive. We say the power factor of the load is 70% inductive. We could also say the power factor of the load is 70% lagging. For capacitive loads, we say capacitive power factor or leading power factor. Same thing. What is that? We're looking at the power curve of a resistor. In it, we see that there is no negative power. There is no Q power. I'll let you read these expressions and come up with the same conclusion. Q in a resistor is 0, and the active power is the apparent power. And that is an inductor. In an inductor, the average power evidently is 0. The inductor only plays ping pong. The positive wave and the negative wave of the power at exactly the same value. In the inductor, active power is 0 and the reactive power is equal to the apparent power. And in the capacitor, let's have a look at the capacitor. Check it out. In the capacitor, the average power is also 0. But look, the reactive power is negative. Is the negative of the apparent power. Negative. What does it mean, a negative ping-pong power? Let's have a look at that. Check it out. Check it out. Inductor, capacitor. Inductor, capacitor. You see something there? Yeah. When the inductor is doing pong, the capacitor is doing ping. So, when one of them is absorbing power, the other is delivering power. So, we could put together a capacitor and an inductor in such a way that they play ping-pong with one another and they leave alone the cables, the transformers, and the generators of the utility. Isn't that nice? That is called power factor correction, and there's a whole chapter we will see in another video that is linked to this one. Tutorial time. Let's say we have a customer. It's represented by all of those elements there. It is connected to the secondary of a power distribution transformer that is represented by that sinusoidal source through a cable that is represented by that RL branch. The question is, use IEEE phasors, that is RMS phasors, right? And compute the RMS value of the current in the cable, that is one. And at the customer, compute what is the RMS value and the phase of the voltage at the customer. Let's begin. The first thing, because I'm going to be using IEEE phasors, RMS phasors, is to find the RMS value of the voltage source. The peak value is 679 volts. The RMS value is that divided by root 2, 480 volts. That means that that source is going to be represented by an IEEE phasor 480 with 30 degrees, like so. Let's define that variable in the calculator, in the HP prime. The voltage source is 480 with 30 degrees. And the impedance seen by the source is computed as we've done many times in the recent past. If we divide the voltage source phasor by that equivalent impedance, we get the current in the source, 80 amps with 4.5 degrees. 80 amps. What amps are those? Those amps are the RMS amperes flowing through the cable and into the load. RMS? How come? We're using RMS phasors for the voltage. Of course, the amps, we're going to get our RMS amps as well. 80 amps is what an ammeter, an AC ammeter, would read if we were to set it up in the middle of that current. That is the first answer. Now they ask of us, compute the voltage of the load, RMS value, and phase. That voltage of the load, see the reference down there, would be the voltage of the source minus the drop in that RL branch. That voltage of the load would be Vs minus the value of the current multiplied by the impedance of the branch, 0.4 plus 1.4J. That voltage of the load is 412 volts with 17.7 degrees. That is RMS, of course. 412 volts RMS with 17.7 degrees. How do I know it's RMS? Because I'm using RMS phasors. All the phasors will be affected by the same factor, 1 over root 2. More. Compute what is the power factor angle at the load in degrees. What was the power factor angle? Theta. That was alpha minus beta. Who is alpha in this case? The phase of the voltage at the load, 17.7. That is alpha. And beta, the phase of the current entering the load, 4.5 degrees. So theta, the power factor angle, we better do that with the calculator because we have all the digits of precision there. Theta of the load is argument of V load minus argument of the current in the source, 13.2 degrees. That is theta, the power factor angle of the load. And they want us to compute also the power factor. The power factor of the load in percent. That is just the cosine of that angle theta, right? Cosine of theta load, that is 0.97. That means that the power factor of the load is 97%. Inductive or capacitive? Well, let's see. The phase of the voltage, alpha, is 17.7 degrees. The phase of the current, beta, is 4.5 degrees. That means that the current is lagging behind the voltage. The power factor is 97% lagging, or it's 97% inductive. Finally, compute what is the active power absorbed by the load. Active power. That would be Vrms at the load, 412, multiplied by the RMS amps at the load, that is 80.15, multiplied by the cosine of theta. We just computed that, right? So the P of the load is absolute value of V load. Hey, wait a second, the absolute value wasn't that the peak value? No, because the absolute value of these phasors is the RMS value of the voltage. Okay. So P load is the RMS value of the load multiplied by the RMS value of the current multiplied by the cosine of theta of the load, that is 32,161 watts. That is P, that is active power, right? So the active power absorbed by the load, the average power, is 32.2 kilowatts. Compute also the reactive power Q absorbed by the load. Oh, that would be RMS volts, RMS amps, and the sine of theta. Sure. Q of the load is V of the load, absolute value, that is the RMS value, times the RMS value of the current multiplied by sine of theta, that is 7,600 VARs. The absorbed reactive power at the load is 7.56 kVArs. And now, for the students in my class, I will ask the same questions but for the source. What is the power factor angle? What is the power factor? Wait a second, because top hat allows only one number answer per question. I will allow you to use a notation that is good only for this question. Don't use it out of this question. You're going to enter the power factor as positive if the power factor is inductive and negative if it's capacitive. Don't use it that outside of this classroom and only for this exercise. Compute the active and the reactive power at the source. These will be top hat questions 1, 2, 3, 4 of power. And it's time for us to take a break. We'll be right back.